We've just been looking at the median and the interquartile range, and the box plot showed us roughly how far off numbers were from median. What we're going to do now is look at how far off numbers are from the average, because this measure that we're going to come up with has deep and useful properties that are used throughout probability and statistics. So let's take as an example a simple little list, 7 numbers, no, 8 numbers in the list. Average is 4.25. There's your histogram. Equal bars at 2, 5, 6, and 7, and then double the size at 3 and 4. And what we're going to do is look at how far these numbers are from their average. Well, the natural thing to do then is to subtract. Take 2 and subtract to 4.25, which gives you, here's the list, and here are all the deviations from average. So that minus 2.25 is the value 2 minus the average 4.25. So here you have a list of deviations from average, and our goal now is to see roughly how big that list is. So let's take a look at that list again. It's the list of deviations. And a natural thing to do is to look at the average of this list. On average, how big are the deviations? And we've done that here, and lo and behold, it is 0. Now, that is both interesting and worrying. On the one hand, it happens to be true, not just for this list, but for every list in the world. If you compute the deviations from average and then average out the deviations, you will get 0, no matter what list you are using. The way to understand that without any algebra is to say each of these entries is one of the values minus the average. And so when you average them, you end up with the average minus the average, and that is 0. This can be shown algebraically, but the thing to take away is that there are some deviations that are negative, corresponding to below average values, some that are positive, corresponding to above average values, and when you add them all up, the total negative deviations exactly cancel out the positive deviations. And while that's true, that's not helpful for what we're trying to do. We're trying to get some sense of the size of these numbers, and so we're noticing that we don't really care about the minus. We want to know roughly how big these numbers are, roughly how big the deviations are, without regard to sign. So let's lose the sign. Now in mathematics, there are 2 time-honored ways to lose the sign. One is simply to lose them, and that's called taking the absolute value. Some of you will know that the absolute value doesn't have great mathematical properties. There is another time-honored way to lose signs. Yes, you've guessed it, you square. You square the deviations, and then all the minuses get squared and become pluses. So here I have a list of squared deviations, and I've taken the average of those, and the average is 2.44, and that is the rough size of the squared deviations. But there's something worrisome about this number. Suppose the list consists of money in dollars, so $2, $3, $3, and so on. Then the deviations are all dollars and cents, so that's $1.75, and that's you owe somebody $2.25. The squared deviations, and hence also their average, are in the units of squared dollars. Now, nobody in their right mind understands a squared dollar. So while we have fixed one of our problems, which is that we didn't want minuses, we have introduced another one in that we are now working in the wrong units. So what are we going to do? We're going to fix our units by doing, yes, exactly, taking the square root. And this quantity, the square root of the average squared deviation, happens to be root 2.44 is 1.56. That is called the standard deviation of the list. And this is going to be the main measure of spread that we're going to use now and throughout the course. So let's go through in words what was done to calculate it. The standard deviation is the root mean square of deviations from average. That sounds like a bit of a mouthful until you read it backwards. Backwards, it is a recipe for producing the number. What did we do? We first took the average. What did we do next? We calculated the deviations from average. What did we do after that? We took the square of the deviations. There they are, all the squares of the deviations. And what did we do after that? We took the average of the squares, and I'll remind you that the average is also called the mean. And that was almost what we wanted, except that we had messed up the units. And so in the end, we took the square root. And that gave us this number 1.56, that is the standard deviation. We're going to spend quite some time looking at that number, understanding what it does, what it measures, how it behaves, how it changes when you change the list, and so on. And why the standard deviation, rather than any other measure of spread, is so commonly used. Before we go much further, let's get some terminology down. Standard deviation is abbreviated to SD because we are lazy. I'm going to go back to our list, and now I am measuring it in dollars. As we had just said, the average is $4.25. And the first thing we did was we computed the deviations, and then we squared them, and then we took the mean of that. So deviations squared mean, that was our 2.44 squared dollars. That quantity has a name. It's called the variance of the list. In the end, as this has the wrong units, we took its square root. The SD is the square root of the variance, and it is the root mean square of deviations from average. And that was $1.56. So it's the average and the SD that have the right units and the same units. And what's good about that? What's good about that is you can add them. You cannot add an average to a variance. But you can add and subtract average and SD. And that's going to be critical for what we're going to do next. I should explain why this mean square of deviations from average, the 2.44 squared dollars, why that has a name. In mathematics, when something has a name, it's usually to signify that it's useful. The way this happens to be useful is, even though physically it is hard to interpret, it has nice mathematical properties. It's related to Pythagoras. You recall that when you have three sides of a right triangle, it's the squares of the lengths that have the nice relation, not the length themselves. That variance has nice mathematical properties is closely related to that. But in the end, the variance is not your measure of spread. It's the SD that is the measure of spread in the units of your data. So we're going to be using the SD. We've calculated a number, and the first question has to be, why? What is it for? What does it measure? It measures roughly how far off the entries are from their average. It measures the rough size of the deviations from average. And to see that in a picture, let's go back to our list and its average and SD now. Here's its histogram again. The average, the balance point, is right here, just above 4. The SD is about 1.5, and what we'd like to do now is to look at the SD on this graph. So you should think of the SD as a plus or minus number, an error of the average. You start at the average and you walk an SD on either side. And so that interval is 2.75 to 5.75. Yes, I'm rounding. 2.75 to 5.75 is right here. And you can see that that interval picks up a good chunk of the list, but not everything. That's not unusual for the range average plus or minus SD, though the percentage differs, and possibly quite markedly, from one list to another. But what is interesting and makes the SD powerful is that no matter what the list, if you walked a few more SDs, so if you started at average and walked 2 SDs on either side, you would pick up a huge chunk of the list. In the case of this list, you'd pick up everything because you would be starting at 4.25 and essentially walking 3 units on either side. So you would go from 1 and a bit to 7 and a bit, and you'd pick up everything. No matter what the list, if you start at the average and walk a few SDs on either side, so say 2, 3, at the most 4 SDs on either side, you will pick up the overwhelming majority of the list. Now, you're not expected to know why this is true at the moment, and I know some of you are very anxious because I haven't defined what vast majority means. Relax, we will. But the main thing to take away from here is that it doesn't matter what the shape of the histogram is. If you've calculated the average and you've calculated the SDs, you can say that the huge chunk of the list is going to be in the range average plus or minus 2, 3, 4 SDs. There will be some stuff outside, possibly, but not a lot. Now, in the next segment, we will make this statement a little more precise. But I want to spend some time now going over some technicalities. The SD is the most technical object that we have met so far in this course, and it is a good idea to examine technicalities so that there are no confusions. Let's take a look at the formula. So how did we calculate the SD? We found the average, then we computed the deviations from average, then we squared the deviations, then we took the mean of the squares, and in the end we fixed our units by taking the root of this mean. We computed the root mean square, also known as the RMS, of deviations from average. And that is the formula for the SD. A formula is just that. It is a recipe. I give you input, you produce precisely the output. If I give you a list of numbers, you can use this recipe to produce exactly correctly the SD. So it is a formula in the language of my choice. Now, people taking mathematics and statistics classes expect formulas to be written in a different language. In that language, the list might have a name like x1, x2, etc., xn. So the x's are the entries, and there are n of them, and the second entry is x2. Let's give the average a name. The average is often called x bar, that flat line over it, consistent with the fact that the average is a smoother. And with this language, the SD has a mathematical formula written in mathematical notation. Ready? Here we go. Now, isn't that pretty? It's awfully impressive, isn't it? But it is exactly the same as this simple little list of English words here. What did we do first? We took the average, so did they. What did we do next? We took the deviations from average, so did they. Xi is a generic value, they subtracted the average. That's a generic deviation. What did we do after that? We squared the deviations, so did they. Here we are, deviation squared. What did we do to those squared deviations? We took the mean, we took the average, so did they. This set of symbols says take the average. Why? Because this sigma stands for sum. It says sum them all the way up through n, all n of them, and then divide by the number that you have. That's our old friend, the mean. And what did we do at the end? We took the square root. So did they. So here are two ways of writing the same mathematical formula. It is the same formula in two different languages. The advantage of the second language is that it is simple and powerful in the sense that it allows you to write fairly complex things in a short space. And if you speak this language, then you can do more complicated mathematics with fewer words. The trouble with it is people tend to get awfully caught up in things that look like this. They get awfully caught up in the calculations, and in statistics they end up forgetting what the calculations are for, what they mean. That's what our course is about. Fine, you can do a calculation, you can do it just as well in English. And then we will focus on what the calculation means. I use both of these when I am thinking about data, whichever one happens to be convenient. You are free to use whichever one is convenient for you. The point is to note that the second one, written in math notation, is no more precise than the first. They are exactly equally precise. Now there's another technicality. A number of you in the forum have been saying you've taken some statistics before, and I am sure that those of you who have taken some statistics or have seen a statistical calculator will have seen somewhere that sometimes people don't divide by n, they divide by n minus 1. Those of you who haven't seen that, please tune out for the next slide. But if you have, let's just take a look to see what that is and why we should use this one instead in 2.1x. So if you have seen this definition before, then listen for the rest of the slide. If you haven't, please go and get a cup of tea. Right, so if you've seen this definition, please don't use it when you're doing descriptive statistics. It doesn't apply. When does it apply? In a very particular situation. Supposing you don't actually have your entire list, you have a subset of it, a sample, and you want to use that sample to estimate the SD of your entire list. Then, if the sample has been drawn randomly in a particular manner, under certain criteria for what makes a good estimate and what makes a bad estimate, it is better to use n minus 1 in this denominator here rather than n. Now I try to type that out, and it takes a lot of words to say that. So it is only in this complex situation that you actually need this, and this applies. When not in that situation, you're not going to be in stat 2.1x. Join me in 2.3x and we will see where it applies. But right now we should not be fussing about using n minus 1. It does not apply. We will take the ordinary root mean with an n in the denominator squared of the deviations and find the SD. All right, all those of you who never saw this before, tune back in please. I'm going to do a calculation with my favorite list in the world, 0 and 1. Oh yeah, a very powerful object, 0 and 1. We're going to calculate the average and we're going to calculate the SD for a reason. What's the average? Yes, it's a half. What's the SD? Well, for that we need the deviations. The deviations are surely minus a half and plus a half. 0 minus the average, 1 minus the average. So the deviations are minus a half and plus a half. What does the SD measure? The rough size of the deviations, without regard to sign, if you recall. Well, if it's without regard to sign, then aren't we looking at 0.5 and 0.5? And roughly what's the size of that? Surely it's 0.5. If our formula is any good at all, when you apply it to this little list, you should get SD equals 0.5, and we are going to check that. So we'll use our formula that says root mean square of the deviations. Here we go. So the deviations are minus 0.5 and plus 0.5. I've squared them, taken the mean and the square root, and the rest is arithmetic. If you square the minus 0.5, the minus sign gets squared, and so you have the same as 0.5 squared. So there's two lots of these. The 2's cancel, and you are left with the square root of 0.5 squared. The square root of any positive number squared is just the number itself. And so, lo and behold, just as you wanted, the SD formula applied to this little list, 0 and 1, gives the right answer. By the way, those of you who have heard about dividing by n minus 1, if you divide by 1 here, you'll get a very strange answer. Once again, don't do it. So that's comforting. It shows that in the simple case, we get the right answer. You can also lift this discussion up to lists that have two kinds of values in them. So here's a problem. Find the average and the SD of the list. Well, here's a list. And I've been asked to find the average and the SD, and I am lazy. If I can avoid doing a calculation, I will avoid it. So the first thing I notice is that there are two kinds of numbers, 480 and 500. And there's an equal proportion of each kind. Half of the list are 480 and half are 500. So if I imagine the histogram, there is a bar at 480 and an equal bar at 500. So where's the average? Exactly in the middle of these numbers, because the histogram is symmetric and so it will balance at its physical center. The average is 490, halfway in between 480 and 500. No calculation. What are the deviations? The deviations are, well, minus 10 or 10, depending on whether you're working with a 480 or a 500. So all the deviations are either minus 10 or 10. If you want the rough size of those numbers, well, you're going to get what? If you disregard the sign, you're going to get 10 without calculation. The SD is 10. This is really a look no hands calculation. Understanding the concept helps you get at the average and the SD. And it also helps you note that the fact that we had 3 of each really didn't matter. You could have had 387 of these guys and 387 of the other kind, and the answer would have been exactly the same, average of 490 and the SD of 10. So while there is a formula and people love to plug numbers into the formulas, and there's a value in that, there is an equal and perhaps greater value in understanding the concept well enough that you can perhaps get the answer exactly by thinking about what it's measuring, or at the very least approximate it by thinking about what it's measuring. We're going to be doing quite a lot of that in this course.